Hello my friends, Roger once again today making a statement that sounds like extreme, over the top, unbelievable, unbridled braggadocio and arrogance. However, it is true. My light research exceeds CERN, and I am going to prove it right now. This lady runs the Hadron Collider, that gigundous thing that goes all around Switzerland right there. She's making statements that I'm going to respond to each one of them. Now, originally they talk about all these different particles. I work with that right there, the electron neutrinos. They work in the heavy particles, which is chunks of the nuclear core. I work with the particles that zip around the outside, which we call light. So now we're going to go into it. I exceed your big Hadron Collider. Alright, I may let her talk about it for a second or two, but it's no big deal to talk about it for a long time. They take huge ring of magnets, a tube, that they can force these magnetic particles to stay within inside this circular tube. They keep exciting them. One goes one way, one goes the other way. And then they crash them into each other, just like hitting them with a gigantic hammer. That is all they are doing, is causing them to crush each other. Listen to me carefully. They are causing them to crush each other. What happens? They break like balls of glass. And they create these spinning disks, which are the Higgs fields, which is nothing more than a particle that has a charge on it. And it's spinning away from here so fast that when it hits the standard air and the particles that are in the air, it concusses with them and creates these fields surrounding them, just like a wire going through, electricity going through a wire and putting magnetic filings around it. It creates identical same field. And guess who's got those? Only we didn't need to do this. We crushed with a Venturi. We didn't head on. We didn't have to even head on. We used light and crushed it into its own self with a Venturi. And I think they can do that too. I think they can do it. I see no reason whatsoever why they shouldn't be able to do that. Alright, now you saw the Higgs bosons. They're identical. There's no difference whatsoever. This is a pulsed red laser, and coming through the Venturi accelerator crusher, which is a particle crusher, they become excited. The wave stretches, they become accelerated into what is called Cherenkov radiation, which is these electron neutrinos. Now they think I won't talk about what they think. I'm going to show you what I think and what I can see and what you can see, and if you have any sense, you'll see it's obvious. We are getting the identical same fields, and these are polar fields. You see the little dots that going around in circles? That means that as this particle is spinning like a zillion miles an hour, it is perturbating all these electrons that are free floating in the air, which are nothing more than the static collects on you, and it's loaded all over the air. They used to call it ether, and then they dropped all that stuff and said, oh, there is none of that. Well, it's all over the place. And it's obvious because it collects on you as a static electricity. It falls to the ground, and the ground is a positive attractive source. I have a lot. I have a new atomic model, has no neutrons. Every single thing works. And it's the only way you can make it work when you go into isotopes and you go into all the variations and all the different atomic weights and all the different spins and all that stuff. And that only can, and it's resonances. It's all because of there's certain resonances, and outside of that resonance, you can't have a certain number of electrons and protons together, or they will fall apart. It's called nuclear radiation, and the nucleus falls apart. It is not resonance stable. I can show this. I can prove every single thing I'm saying. So, I have the picture of electron neutrinos. Let's see what CERN has to say about their abilities, which they can't see these. They say, well, there's no way we can see these. Well, I'm looking at them. First of all, I'm going to prove to you that what I was showing you was Higgs bosons, because I am going to show you every bit that proves it. This is standard light going through the air. No big deal, just going through the air, sort of glowing. All of these little white particles, this of course in the dark, all these little white particles are glowing ether, these little white ones, because they're extra electrons and they're concussing. And when they concuss, they glow. And that thing coming through is concussing them because it owns a huge region in space. And as it comes through, it's get out of my way. And they all glow because that is the nature of concussion of light. All right, so now the same wave becomes elongated, stretched very violently. The particles become concussed into each other and display as particles, creating plasma, crushing each other, identical to what CERN does. Identical. They're just going this way and this way with heavy particles. They explode like hitting two hammers together. We are forcing these to do, I think, more than that, because you can see the plasma that's coming out of here. It's absolutely stunning, the amount of plasma that's shooting out of there. And that plasma is nothing more than raw electrons that want to be away from each other because they own this region. They don't want to be touching each other. They don't want to be invading each other. That's why they glow. That's why electrons glow. And not only that, my friend, these electrons are dipoles. They are not just negatives. All right? I'm going to show you. And my electron flood theory says protons are identical, only they are positive. I have it very well worked out too. This is a dipole. It's obvious it's a dipole. I think it is a torus, and it's doing a right-hand rule spin. Not only is it a dipole, it is a box. It is a square. It is a cube, and it has polarities on all sides. It is an elegant little pattern, and cubes have the best polarities to create magnetism. Those, when you look up cubic molecules, or cubic elements, the cubes are the ones that have the extreme magnetism capabilities. Now, I'm going to show you what it looks like in my little diagram. Hold on. All right, I think you can see that. Oops, hold on a second. Now you see the red and the black dots. That's positive and negative, spots. Right, and they attract each other. These attract each other. These attract each other. One's on the other side. This whole block, top, bottom. It's an elegant little design. And when you smash into this, it forces the field to excite and glow. I cannot explain that, but it happens. All right. Now, one more thing for CERN. They couldn't see these. We can see these. The electron is literally in the center of these dots, and it is the particle. That is the same particle as the particle that are inside these fields, but that one is spinning in reverse. The other ones are doing the right-hand rule. That one's going backwards and gathering its field into itself. And guess what happened when that impacted with a standard Higgs field? All right, that's what happened. That is that white particle. That is that reverse spinner. It came down here. Now it is reforming into its own field and spit off a part of an electron. Now, I don't know what CERN is thinking about, but this is an electron, which they can't even find. They say it's too small. And this is obviously not as big as that. So what is that? I got a lot to offer here. I could show them things that they don't understand. And I'm going to show you that she says she doesn't understand.
July 2012, we were treated to a summer blockbuster in this story. The final piece in the hunt for the Higgs boson. On the French-Swiss border, close to the city of Geneva, the biggest experiment ever built by humans was at the center of attention. For a little over 2 years, the Large Hadron Collider at CERN, also called the LHC, had been taking protons and accelerating them to almost the speed of light, both directions, around a 27-kilometer long tunnel, and then smashing them together in the center of carefully constructed detectors. Here is one of those detectors, and indeed it's the experiment that I work on. It's called the Atlas detector, and it's one of two general-purpose detectors on the LHC, which you can think of like a giant particle camera. It's 44 meters long and 25 meters high. At 1,000 tons, it weighs as much as 100 747 airplanes.
All right, that's their camera. They go here and there, and they smash them together, and they see the particles that go. Well, I mean, I don't want to embarrass anybody, but I'm going to tell you what. This is what we use to accelerate our particles. It's a pulsed red laser that you can also use to do construction. Now, it shoots out a red beam, red laser beam, and it pulses. And I showed you what it is, and here is our camera. Any cell phone camera will take these pictures. Totally unmodified, no problem. So there's what they're using, and this is what we used. Of course, we got a little better quality pictures, but anyway, here goes.
Airplanes. In fact, it's so big that I had to make a slight alteration to the standard unit of measuring the person. Although I might get in trouble with a certain few scientific friends for putting people and dinosaurs in the same diagram.
He.
So how does this particle camera work? Well, often the first particle created in the proton collisions, like the Higgs boson, it doesn't live for very long, and it quickly changes into lighter particles.
Exactly as I show, we get two waves, and then it crashes back into the lighter particles, which it was normal.
To find out what this first particle was, we have to measure these secondary particles that come out in all directions. So, to do its job, Atlas is made up of layers, like an onion.
All right, she's talking about the layers of absorption. Now, don't forget, I claim the nuclear core is made up nothing more than little tiny bar magnets. They're those little light particles, only they're positive and negative. They're exactly the same size. And I did the calculation. It works out to be 918 of the positive ones and 919 of the negative ones for every proton mass. Well, actually, for every neutron mass, because neutrons don't exist. And of course, protons are just 50-50. And when you add the neutron, that makes you a negative core. That gives you your orbitals that surround that negative core. So she's talking about chunks of, like they're hand grenades coming off of well, here, let me just show you something. Hold on. All right, this is what I'm claiming is the nuclear core. Nothing more than a ton of little bar magnets that are together, and you can't break those apart. But there'll be other ones that are floating around out here. They can't get in because there's more negative in here than positive. So the negatives push the incoming ones to float around in their orbitals, and they become elegant. Now, if you don't have the right resonance number, and that is, they go by these different chunks, exactly like frequencies do. Wavelengths of frequencies are resonant frequencies. That's why harmonious and notes and things like that are perfect. But once you get out of that number of vibrations, then you got a problem. What is the number of vibration? It's the number of these. And you may end up with something like this. All right, it's not hanging in there. Get out of here. Well, I want to stay. No, get poof. It goes. That's nuclear radiation, radioactivity. Okay, so back to CERN.
An onion. And we'll start from the center and work our way out, like the particles. So this is called the tracker. When a particle with an electric charge passes through, it leaves electrons in the tracker, showing where it's gone. When we combine this with a magnet, which bends lighter, slower particles,
You heard what she said. The magnet bends them. Now, she's going to be talking about spin. I think they're spinning some to the left, some to the right, and the magnet will determine which way they go, and that's how they determine the spin character, which is nothing more than the positive chunks or the negative chunks.
More than heavier, faster ones. We now start to learn something about the particle's mass. Also, since negatively charged particles bend one way, and positively charged particles the other,
There you have it. They're nothing more than little chunks of bar magnets in there.
we now know something about the particle's charge. The next section of our detector, or layer of the onion, is called the calorimeter, and it measures the energy of the particles. Up until this point, we've tried not to destroy anything, but now the only way to accurately measure the energy of the particles is to get it to give it up.
All right, they're going to smash them into tiny little bits, and that's where they get these chunks of the core. The chunks of the core are heavy because when you make a resonant stable proton, which, as I said, 918 positives and 918 negatives, is like that's a bar magnet. And when it's resonance stable, they stay together pretty good. You really got to smash them to get them apart. And they sometimes come out in 2s and 4s and 8s and 10s and 12s or whatever. They're radioactive because they're not stable, but they are in chunks. They're like little hand grenades. When they go out, they poof. So here she goes.
We do this by alternating layers of an absorber, such as lead, to get the particle to release its energy, and layers of a detecting material to measure it. After these sections, we should only have 2 types of particles left from our standard model. The first of these are muons, and these are the heavier cousins of electrons.
All right. This is the key. Listen to this. It will blow your mind. She's talking about muons and she's talking about electrons. I am using electrons. They are using muons. I am getting the identical Higgs patterns because all particles are the same. They're all the same. They don't realize this. They're smashing these things into bits. They are looking for the same particles I'm looking for by crushing the tiniest particles. But then find out that the tiniest particles can get even tinier. Here she goes. She's going to admit they cannot see the particles that I am talking about because I'm only using light. I am not using anything heavy. So don't tell me I'm doing anything different than finding light particles turning into bosons, Higgs bosons. Here goes.
They are 200 times more massive and very difficult to stop. So we have a layer on the outside of our
All right, that's 200 times more massive than an electron because they can't find electrons. They really don't even care about them hardly.
detector called the muon detector, which just measures these particles. The second type of particles we have left are called neutrinos.
All right, neutrinos, that's my realm. Here goes.
These are extremely light and don't interact with any part of our detector, and so they travel all of the way out. The only way we know that they are there is from the conservation of momentum.
You could have called me. I'll tell you they were there. I could show you they're there.
Mass times velocity. This tells us that if we have a lot of momentum in this direction and not so much in this direction, it should have been equal, and so there must have been neutrinos over here.
All right, well, there were, and I showed them, and here they are. All right, right out of her mouth. They can't find the electron neutrinos. They create electron showers. It's exactly what I have shown. We have created the Cherenkov radiation because that is a high-speed particle. Whether it comes in high speed and crashes into the regular air, or we accelerate it and it crashes into regular air, it does not matter. It still creates the electron showers, which I show in many, many, many cases. And they are created from the red or from the green. I will show you that. The CERN can only pick up these muon neutrinos. You heard her say this. It's not my words, that's her words. Same Cherenkov radiation causes this to happen, but it's with the heavy particles. Cherenkov radiation happens this way, but they're very, very tiny particles. Words from her mouth. All right, this is the green shower, and I think Rodney took these pictures, and I think this is with a non-pulse, a continuous wave laser green. But the green is extremely more powerful than the red, and I'll show you not only in the disk excitation. Let me show you something else. All right, now I don't know if these discs are not, I mean, are much clearer than the green because they are not moving as fast, or that, you know, they're less impactful, and they're easier to pick up. Let's say, I don't know if that's true or not. I'm just speculation, but I'm seeing the green, I'm seeing the red. They are the same architecture. The particles are also the same. All right, the only difference between the green and the red that I can find, it comes out of the accelerator here all blurry and in chaos, and then it quickly settles down, the red, because they don't have the impact power. Still, you have that same particle. There's no difference whatsoever. It's a dipole. So this is red, and they're supposed to be lepton colors, and I think I agree with that. There's red, blue, and green. Now there's the green. You see they're coming way, the accelerator's way down there. And believe it or not, this is full spectrum sunlight with a guy, Renz, my friend, just holding his thumb up like this, and the light is now being semi-accelerated just like an airplane wing. What is happening? The Higgs fields are tumbling off his thumb because it's a half a Venturi. It's spinning off. And if you look carefully in a high resolution here, you can see the blurriness of that light. It's literally liquid, then presenting itself. These blue, green, red, tiny, thicker, longer, tiny, thicker, longer. And as they come further, they're impacting more and more and becoming stretcher and stretcher until they become less normal. And stretcher, I know, is not a word. Now, that is the nature of light. Leptons, they say they're blue, green, red, and they can make every color with blue, green, red. And black, my friend, is not the absence of color, it is the absorbance of every color. That's what black is. It's not there's no color there. Every color is there, but you can't see them because they're all mixed together. That's why it does not emit. It sucks in every electron, because these are nothing more than electrons. That's an electron right in there. Electron right in there. Black says, give me it, I'll take it. That's coming in white, and they predicted that. I was surprised, to be perfectly honest with you, that the disk was white. I haven't seen a white one. But in full spectrum, they say any Higgs will be white, and that's right. Now, I think they discounted this, because that went back a long time ago, this particular article or paper, whatever it was, talked about these lepton colors and this white Higgs. So this is not pie in the sky here. This is actual serious action here. And all that was a thumb up against the sun. So if his thumb was the size of my thumb, all right, so he's a little bit bigger than that. So that disc is maybe this big around. In reality, it's that big around. These are not tiny little things. All right, this is the progression from pulsed red laser to accelerated red laser to particles, okay, to ether everywhere, to reverse EMF of enormous proportions, to plasma, to the interference patterns, which are not from waves, they are from repulsion, magnetic repulsion, out the Venturi to the Higgs bosons, which are the boson charged particles, with the spinning particle heads, which are, spinning field heads, which are the Higgs fields. And that is due, and they snap like that quickly back to normal light. This is due to this accelerated particle slamming into unaccelerated space, fluffing up that field, which is the particles spinning around it, which are nothing more than free electrons. This is a field that crashed into the white particle, which is a reverse spinner. Nobody knows about that particle. That's a new particle. And that is a portion of light. So all of this is so far over the edge, but it is better than CERN. We're on top of CERN. This is my entire setup. I'm going to show you what we use for the whole thing to do this. Now, I'm not trying to embarrass anybody, but I would be embarrassed. That's what we use. That's what we use. Right? So they can ignore, and they can just keep doing what they're doing. But I think I have the correct model now, and it's made up nothing of these. All of these, they're plus ones and minus ones. Case closed.